Hello everyone, welcome back. This is the fifth video for Chapter 9. However, it's not going to cover any additional content. We're just going to go through a couple of example problems, putting everything from this chapter together. And so we're going to look at two different example problems involving collisions. And when it comes to these collisions, there are two types of conservation laws that we want to look at. We have the conservation of energy, and we have the conservation of momentum. And it is the conservation of momentum that was introduced in this chapter, which says that the momentum that we start with in the system has to equal the momentum that we end with in the system. And typically this is in reference to a collision. So if we have two masses that start with a certain amount of momentum and then those masses collide, the momentum or the net momentum that they carry after the collision has to equal what they had before the collision. And then our conservation of energy expression, which we had back in chapter 7, says that what energy we start with has to equal the energy that we end with. And we could modify this energy equation to include things like thermal energy, sound, light, etc. But if we do that, our ability to keep track of all those different types of energy becomes more and more difficult, especially since the only energies that we've discussed so far have been kinetic energy, potential energy, and thermal energy. We haven't actually talked about sound or light energy. That would be better suited for a different course, actually. And we mentioned in the last video that when it comes to collisions, there are two types of collisions. We have the elastic and the inelastic collisions. And the inelastic collision is what we see up here with this energy expression. With an inelastic collision, we do not conserve the mechanical energy of the system. And we know this because if there's any heat generated by a resistive force like friction or air resistance, then that energy has to have come from whatever mechanical energy that we started with. And mechanical energy was just the combination of the kinetic and the potential energies in the system. Whereas for an elastic collision, we would conserve the mechanical energy, and that means that there would be no resistive forces in the system, so no friction, no air resistance, but that makes for a pretty unrealistic system. So almost all collisions that we're going to consider are going to have to be inelastic in nature. But we can use the elastic case as an estimate. And we'll talk about what that means later on in the video. For right now, we just want to get this first example problem set up. And what we're going to do is we're going to jump in our time machines and go back about 150 years, and we're going to work in an ammunitions factory. And it's going to be our job to test the muzzle velocity of the bullet that we're making. Now, the reason we want to go back in time is so that we're forced to use the physics that we have at our disposal right now. If we were to do this today, what we would do is we would set up an apparatus with 2 lasers. We would fire the bullet through that system of lasers, and at the other end would be a set of detectors. And these detectors would be tied into a computer, which would be measuring the intensity of each laser beam, but the computer would also be timing the system. And so as the bullet would pass through the first laser beam, we would see a dip in the intensity of that laser beam. And then the computer would mark that with a time value. Then the bullet would continue and pass through the second laser beam. I'll use a different color for this one. And we would see another dip in the intensity of the beam, and the computer would assign a time for that as well. We can measure the displacement from one laser beam to another. In fact, I should probably draw that as a displacement vector. There we go. Our basic definition of velocity is displacement over time. And we know what the time interval is because we've had the computer taking that measure for us. It's going to be a lot easier for the computer to measure the time interval than it is for us to try and take a measurement by hand. We're probably not even going to see the bullet as it passes through those lasers, but the computer is going to be able to take those measurements far more efficiently. And so combining the displacement between the lasers and the time interval, we get the velocity of the bullet. Now we do want the displacement between the 2 lasers to be fairly small, maybe 10 centimeters or so, because believe it or not, air resistance does slow the bullet down quite a bit. But this will give us a pretty accurate value of the muzzle velocity of the bullet. But as I said, we're going to jump in our time machines, go back about 150 years where no one's even heard of a laser or a computer. And we need to figure out how we're going to safely measure the velocity of this bullet when it's fired. And the way we're going to do that is we're going to use something called a ballistics pendulum. So we will go out into the woods somewhere. We'll cut down a tree and get a log segment, and we'll hang that log segment from the ceiling. Now we would want this to be a fairly fresh cut log, because if we use something that's too dry, the bullet could potentially shatter the log as it goes through. But if we use this wet or green wood, then the bullet is more likely to become lodged within the log. And that's what we want to happen. This is obviously a collision when the bullet collides with the log. And so during that collision, there is going to be a transfer of momentum and energy from the bullet to the log. Now we have the log hanging by some ropes from the ceiling, and after the transfer of momentum and energy, the log is going to have some velocity after the collision, which will then begin to carry it forward. But because the log is anchored to the ceiling, the path that it takes is actually going to be one of a slight arc until we reach some maximum height. So there will be a noticeable change in vertical position for the log as it swings until it reaches that maximum height, at which point the final velocity of that log is going to be 0. Now keep in mind the bullet is still lodged inside that log. But from this point to this point, there is no collision. The collision has already occurred. The collision is over with. The only thing that's happening now is a displacement. The log and the bullet are moving together from one location to another. And as that happens, there is going to be a noticeable change in the potential energy of the system because we're changing the height. And we know that if we change our potential energy, then we're also going to have to change the kinetic energy. And we should be able to see that from this diagram as well. We start with some amount of kinetic energy right here after the collision, and then we're going to lose all of that kinetic energy in favor of potential energy. So what I'm going to do is I'm going to label some specific points within the diagram. The first point will be right here. I'm going to call this point 1 or location 1 in the diagram, where the bullet has just been fired. And so the only thing in the system that has any momentum or any energy is the bullet. Before the bullet strikes the log is just hanging there. It's not moving, doesn't have any momentum, doesn't have any energy. Then we will have location 2. And this is going to be the point right after the collision. So after the collision, the bullet has transferred energy and momentum into the log, and the log is being carried away with this velocity right after the impact moment. So let's update this, and let's say that this is the velocity of the bullet at site 1. This will be the velocity of the log and bullet at site 2. And then up here, when we reach our maximum height, that'll be site 3. As such, we have a velocity at site 3, which is just the final velocity of 0. When it comes to conservation of energy, we can compare the energy at any site. For a closed system, the energy has to be constant. If we can track the different states that the energy is in from one point to another, then we can use conservation of energy to do the physics. The problem with using conservation of energy is between these two, because during that collision, as the bullet is digging its way through the log, there's going to be a lot of friction slowing that bullet down, and that friction is going to generate quite a bit of thermal energy. And that thermal energy is not something that we're prepared to measure in this given situation. I'm not gonna. I don't know how to measure the coefficient of friction within the log and the bullet. Trying to measure the displacement of the bullet through the log could be a bit of a task. And so trying to use this approach for a collision is not a good idea, because there's a lot of thermal energy that's going to be lost. And this equation right here does not take into account thermal energy. I would have to add it in. And I'm not prepared to do that right now. Instead, could I use conservation of momentum between sites 1 and 2? And the answer is yes. We should be able to use either of these conservation laws. The question is which one is easier for us to use in a given situation. When it comes to momentum, momentum doesn't care about the energy. It doesn't care what kind of energy you have. It doesn't care how the energy is transferred or transformed. And so if we could conserve the momentum between those 2 points, then we could do the physics. The one thing that we have to make sure of is that in addition to having equal numerical values on each side, do we maintain the vector direction? Because momentum is a vector. Well, let's take a look. Before the collision, our bullet has a velocity that is to the right. If we need to set up a reference frame, we can. And then immediately after the collision, the log with the bullet lodged in it has a velocity that carries it to the right. And so yes, we do in fact maintain a constant. I don't know why this box keeps popping up. We do maintain a conservation of momentum. All we need to do is put together an equation now that describes what's happening. So let's clean this up. Since we're not going to be using the conservation of energy between sites 1 and 2, let's use conservation of momentum. So for site 1, 1 being the point in the problem where the bullet has just been fired out of the gun, we have the mass of the bullet, which I will call little m, times the initial velocity of the bullet, which we are calling v1, plus we have the mass of the log and whatever initial velocity that log has, but we know that it's 0. The log is initially just hanging from the ceiling, not moving, so that's 0. That's the initial momentum of the system. It's all being carried by the bullet. We then have to set that equal to the momentum immediately after the bullet becomes lodged in the log. We now have a combined mass of the bullet and the log. We'll assume that we didn't lose any mass from this collision. We'll just assume that the bullet kind of pushed the wood fibers out of the way. Again, this is why we don't want a dry log, because we could end up shattering it. But it's this combined mass of the bullet and the log which will then travel away with this velocity that we're calling v2. So just to summarize what we have here. That's the conservation of momentum between sites 1 and 2. I haven't given any values yet, but if we need to, since this is your job to test these bullets, keep in mind the things that you can control in an experimental setting. We can control the mass of the bullet, and I'm going to say we have a 10-gram bullet, so that would be 0.01 kilograms. Another thing that we can do is we can control the mass of the log, because we went out, cut the tree down, we can cut the segment of log and we can measure the mass of that log. So maybe this log is 5 kilograms. So those are the two things that we can control. Ultimately, we're trying to find this muzzle velocity of the bullet. But the only thing stopping me from solving for that is I would need to know what the velocity of the log is after it has been shot by the bullet, and I don't know that. So we're kind of stuck, but this equation is ready to go for whenever we find out what that value of V2 is equal. So let's see if we can find out. We're going to go back up to our picture. We've used conservation of momentum between sites 1 and 2 because there was a collision there. Conservation of energy does not work well during collisions because of that uncertainty as to how much thermal energy or sound or light could potentially be produced. So now we're going to go between sites 2 and 3. As we go between sites 2 and 3, the only thing that's happening here is that we're displacing from one point to another. Now look at how your velocity vector has to change as we displace. Our velocity vector will have to continuously change direction as the log swings. Now, conservation of momentum is always true, except we're going to have a very difficult time trying to conserve the direction of this ever-changing vector. And so conservation of momentum is probably not something that we want to use between sites 2 and 3. However, we've done plenty of problems in the past where we can conserve energy by moving from one location in space to another. Because our conservation of energy equations, the only thing that they care about is how fast we're moving and where we're at. And that's true on the other side of the expression as well. How fast we're moving and where we're at. It's going to be far better for us to use a conservation of energy during this displacement. So, when we have a displacement in our problems, it is best to try to use conservation of energy, because if you start moving around in 2 dimensions, 3 dimensions, it's going to be a real chore to keep track of the vector directions of your momentum. Whereas for a collision, conservation of momentum is the way to go, because we can't really effectively keep track of all the energies during that collision. All right, let's see what we have for energy at Site 2 versus energy at Site 3. At Site 2, we have some combination of kinetic and potential. Likewise, for Site 3, there are no springs involved in this problem, so the only potential energy that we need to concern ourselves with is gravity potential, but gravity potential does need a 0 point. And we'll go ahead and designate a 0 point for gravity. And I'm going to go ahead and use the lowest point in the system. That's going to be where our gravity potential is 0, and then I can define anything above that as a positive value. The kinetic energy at Site 2, so this is immediately after the collision, and this is where the combined mass of the bullet and the log begin to travel away with a speed of v2. The potential energy at Site 2, well, at Site 2, we're at the 0 point for potential energy, so that's 0. And that's it for energy at E2. At E3, we have some kinetic energy based on the speed at 0.3, but we're at a maximum height, so that speed is 0. That means our kinetic energy at Site 3 is 0. And we have the combined mass of the bullet and the log, which achieves a maximum height of h. And so we have two equations for this system. We have a conservation of energy equation that tells us what's happening between Sites 2 and 3. We have a conservation of momentum equation that tells us what's happening between Sites 1 and 2. Of all these sites, Site 1, Site 2, Site 3, which one would we have the most information about? Well, so far we only have the masses of the bullet and the log. But in the experiment itself, the point of the experiment is that we want to measure the height of the log after it swings and comes to that momentary halt. And so we could have somebody standing off to the side watching to see how high that log swings. Maybe we could attach like a pencil to the bottom of the log and have it trace a line on the wall as it swings up. But as we do that, let's say that the height of the log after it's shot is 8 centimeters. So we know the two masses and we know the height of the log at location 3. So that means right here, this is where we have the most information. In fact, we've got all of that information. We have a bullet that is 0.01 kilograms. We have a log that is 5 kilograms for a combined mass of 5.01. We have G, and we have 0.08 meters for the height. All of this is going to go into our calculator. Get the calculator app open. 5.01 times 9.8 times 0.08. This equals 3.93. Keep in mind that this is from our conservation of energy equation, so this means we have 3.93 joules of energy present at that location. That has to equal the same energy that the bullet and log have when they start swinging at location 2. And now that I know what that energy value is, I can solve for the value of V2. In fact, in this particular case, it's not even required that we know the combined mass of the two because it factors out. So if we wanted to, we could just jump right in to solving for that velocity without even having to know how much energy there is. And that's kind of nice. V2, if we rearrange this with our algebra, we get root of 2gh. So V2 becomes 2, 9.8, 0.08. 2 times 9.8 times 0.08, and we have to take a square root of that, which gives us 1.25 meters per second, which doesn't sound all that fast. You know, that would be the equivalent of a brisk walk for someone. But that is not the velocity of the bullet. That is the velocity of the bullet and the log. We can now take that velocity and plug it into the conservation of momentum equation that we had. And what we're going to see here is that the magnitude of the initial velocity of the bullet means taking all of the momentum that the bullet and the log had and cramming it back into just the bullet. So we have that combined mass of 5.01. We had the velocity of 1.25, but now we're going to divide that by the very small value of mass for the bullet. And that results in a velocity of 620, I'm going to round that up to 628 meters per second. So almost 6 1/4 football fields in 1 second. And so that's pretty fast. And I'm going to get my phone to look up the speed of sound. Speed of sound, meters per second.
One speed of sound is equivalent to 343 meters per second.
All right, so we have a bullet that is just shy of Mach 2 in its velocity. I have never heard anyone complain that a bullet was too fast. To answer your question, yes, there is such a thing as supersonic ammunition. These are bullets that hunters can buy so that when they fire at their target, the bullet gets to the target before the sound of the gunshot does. For obvious reasons, this would be useful in military applications. But if you wanted to change the velocity of the bullet, maybe Maybe you want to slow it down, maybe you want to speed it up. Well, what could you do? And there's a couple of different things that you can do. One thing would be um, to add more. See if I can do an accurate representation of a bullet here, because you've got the shell casing with all of the powder in it, and then the bullet itself is just the actual case, or not the casing, but just the solid portion. Everything else, the shell and the powder, remains behind, but it's that powder and the interaction with the powder and the hammer from the bullet that is going to expel the bullet with its muzzle velocity. So you could put more powder into the shell. You could produce a longer shell, but that would mean probably having to redesign the firearm to accommodate a larger shell. You could make the bullet smaller. If you had a bullet of smaller mass, then that would increase the velocity of the bullet. But this was a very common method of measuring the muzzle velocity of a bullet, and it was a basic use of physics, and it was a safe method. You didn't have to have anybody up close to this apparatus to do the measurements. Obviously, today it's going to be far more efficient to use the laser apparatus, but you could still use something like this. I wouldn't recommend it. It's our public safety announcement. Don't play around with firearms. But that brings us to the end of the first example problem that I wanted to show. The second one is going to be similar to the first one, in that we're going to fire a bullet into a block. But this time we're going to fire the bullet into the block from underneath. So we're going to fire the bullet into the block. We'll have a little partition in the table here where the bullet can pass through. And the initial velocity of the bullet, we'll say, is 300 meters per second. But this particular block is made of a softer material than what the log was. And what's going to happen in this case is that the bullet will actually pass through the block, and it will exit with a final velocity of 200 meters per second. So if the mass of the bullet is little m and the mass of the block is big M, what will be the maximum height that the block achieves after having this bullet pass through it? Now, if we want to add some values to this, we can. We'll do another 10-gram bullet. But this block, we'll say it's 10 kilograms instead of just the 5. So what's the maximum height? Like the previous problem, there's going to be a couple of different sites that I'm interested in. What we have here is basically a before and after picture of what happens to the bullet and the block during the collision. And so after the bullet passes through the block will have some initial velocity carrying it upward. but then we're going to reach some maximum height where the final velocity of the block should be 0. So our points of interest are going to be, number 1, just before the bullet strikes the block. Number 2, just after the bullet emerges from the block. And then number 3, where the block reaches its maximum height. Now, one major difference between the two problems here is that the bullet is gone. After the bullet passes through the mass, it continues traveling up and it's gone. It's no longer part of the problem. But it is part of the collision process. So we need to take that into consideration. So for sites 1, 2, and 3, we need to get some math that we can compare the different sites to. If we go chronologically from site 1 to site 2, is it better to use conservation of momentum or conservation of energy? And so if we go back up here with the previous problem, we said that for collisions, it's better to use conservation of momentum. And for displacement, it's better to use conservation of energy. So that's what we will do. Between sites 1 and 2, that is a collision. So we will use conservation of momentum. Why does that box keep popping up? It's annoying. Between sites 2 and 3, the bullet is gone, the collision has already happened, and so now all we have is a displacement of the box going from the tabletop level to the maximum height. So that's a displacement. And we would be much better to use conservation of energy between sites 2 and 3. So let's put some equations together. At site 1, we need the combined momentum of the bullet and the block before the collision. Switch back to regular. There we go. We have the mass of the bullet times the initial velocity of the bullet plus the mass of the block times the initial velocity of the block before the collision. Now, before the collision, the block should just be sitting there, not moving. And so there should be 0 momentum associated with the block before the collision. After the collision, so maybe we should specify, well, if we can say that velocity of bullet at site 1, that's the 300 meters per second. Velocity of block at site 2, that's after the collision. So we'll have velocity of bullet at site 2. We should probably put in some subscripts here just to make sure that everything is labeled properly. All right, so just to recap, at site 1 we have mass of bullet, velocity of bullet at site 1 plus mass of block, velocity of block at site 1, which is 0, equals, so now we're after the collision, so we're at site 2, and we have mass of bullet, velocity of bullet after the collision, plus mass of block, velocity of block after collision. This is a conservation of momentum, so these are all vectors, but everything looks like it's in agreement. We start with momentum upward. We end with what looks like a total momentum that is upward for both the bullet and the block. So this all looks okay. And when it comes to the numbers, we have all of the numbers except for the velocity of the block just after the collision. So let's take those numbers and we can put them into our equation here, and we can solve for the velocity of the block just after the collision. We're going to have the difference in the momentum for the bullet. So here we can see that the bullet is losing momentum in favor of giving some of that momentum to the block. And we'll have to divide by the mass of the block. So the mass of the bullet was 10 grams. The bullet went from 300 to 200 meters per second, and we have a 10 kilogram block. Put all that into our calculator. 0.01 times the difference in those is 100. So we're at 1 divided by 10. Gives us a velocity of 0.1 meters per second. So the velocity of the block after the collision is, that works out to be about 10 centimeters per second. So what height will that block achieve? From site 2 to site 3, that's a displacement. We said we could use conservation of energy. We're going to look at the energies at site 2, compare them to the energies at site 3. At site 2, now keep in mind that we're only interested in what the block is doing. The bullet is gone. We're just interested in what's going to get the block to its maximum height, and that is going to be the mass and velocity of the bullet. I just said exactly what I didn't want to say. That is going to be the mass and the velocity of the block only. The bullet is gone. Repeat, the bullet is gone. It is not part of this expression. I need to know the potential energy at site 2. Well, at site 2, this is when the bullet has just passed through the block. Again, we're only interested in the block. So where's the block? Well, it's still at ground level, and we need to designate a 0 point for potential energy. I'll go ahead and let that be ground level. Potential at site 2 is 0. That has to equal the energies at site 3. When we get to site 3, our kinetic energy should be 0. And that means that our block reaches that final height of h. In this case, we do not need to know the mass of the block because it's going to cancel out. And so the height of this block is going to be velocity of block from site 2 squared over 2g. I'll put some numbers into that. We had 0.1, that was the velocity, squared 2g. So this height is not going to come out to be very, very large. We have to square what we have, then divide by 2, then divide by 9.81. And so, not very dramatic. We're getting 0.0005 meters, which is effectively half of a millimeter. So nothing very dramatic there. We fired the bullet through this block, and the bullet just kind of looks like it shakes a little bit and doesn't go anywhere. So how could we make that more dramatic? We could change the difference in the velocities of the bullet. We could reduce the velocity of the bullet when it exits to something like 100, but that's not really something that we can control in this experiment. What we could do is we could reduce the mass of the block that we choose to use. I'll reduce the mass of the block to 1 kilogram as opposed to 10 kilograms. Now, how is that going to affect things? Well, the first thing that it's going to affect is the velocity of the block after the bullet has passed through it. So instead of having the mass of 10, we're going to turn that into a mass of 1. And that means that the final velocity of the block after it has the bullet pass through it is going to be 1 meter per second. That value will then go into the conservation of energy expression to tell us what the height is going to be. So now that our velocity is 1, we have 1 squared divided by 2g, which should end up being, I think, half of a centimeter maybe. Let's see, 1 divided by 2 divided by 9.8. Nope, it's 5 centimeters. Yep. Okay, so that looks a little more impressive. If we could get this block to jump up about 5 centimeters. So that's the end of the second example problem. Basically, we've done the same problem, but we started at different ends of the math. For this problem, we started with a lot of knowledge about how the momentum in the system changed, and we then used that to tell us how the energy of the block was going to transfer or transform so that we could get a maximum height. Whereas for the ballistics pendulum problem, we started by knowing the max height, and we worked our way back to figuring out what the initial velocity was by comparing the energy of the log and the bullet to the change in momentum for the bullet itself. All right, so that brings us to the end of Chapter 9. We have one more chapter for the semester, Chapter 10. So we will see you at Part 1 for Chapter 10.